We only have a couple more fields left, and the next one we're going to talk about is the TTL field, which stands for time to live. You'll see that's on the third row there. It's the 8th byte offset from 0, and it's a single byte field. Now, to talk about TTL, I want you to think a little bit about our discussion of routers earlier. And we talked about, when you communicate to something out on the internet, your packets may traverse a number of routers, dozens or more routers, to get to their destination out on the internet. And some routers have static routes built in, and they say anything coming from a certain place or going to a certain place always takes a specific route. But for the most part, when you get up into the ISP level and higher, you're going to encounter dynamic routing, right? So routers will try to automatically choose the best path to send your packets, whatever's going to be the fastest. And this has a couple of different benefits. One is obviously speed, but also another is also resiliency. If a link goes down, these protocols will basically determine what link would be better suited to get your packets to where they're going. So it's making the internet a little more resilient, making it to where your packets will get where they're going, even if a certain link segment is down. Maybe there's a big power outage somewhere, some farmer with a tractor cut through a fiber line somewhere. Sure knows, I saw enough of that in my time in Kentucky. So it's all about rigidity in that sense. Now, the thing with that is, what happens if I send a packet out across the internet and it finds a misconfigured router, or maybe a couple of misconfigured routers, and let's say one router is configured to send it to another router and that router is configured to send it back, and that just keeps going, right? There's this endless loop of this packet being transmitted back and forth between a couple of different routers. Well, what would happen there without the TTL field? Well, what would happen is those packets would just build up and build up and build up, and eventually it would overwhelm the link and shut the whole link down and denial of service everything. And when these errors can be pretty prevalent, even at small scale, it doesn't take a lot of packets to really gum up the works, so to speak. So the TTL field is really a mechanism that's meant to not allow that sort of thing to happen. It's meant to give packets a maximum lifetime, so to speak, so that if they get caught up in some type of endless loop like this, some type of routing error where they're just being bounced around aimlessly, then they'll eventually expire and be discarded completely, and that data will just be dropped. So that's what TTL is. And of course, it says time to live. Per the protocol spec, it is actually based upon time. It's a time-based protocol, but in practice, generally, we see time to live based upon the number of hops that a packet goes through. So as a packet is transmitted, it's transmitted with initial TTL value, and every router that it goes through decrements that TTL value by 1. So it decrements that hop value. So if the initial value is 64, it can go through that many routers before that value is decremented to 0. And once it's decremented to 0, the packet's dropped, and the router that's doing the dropping will send a response back to the originator, an ICMP response. So let's talk about that a little more. But again, note that this is in the IP header, 8th byte offset from 0. You see it right there before the protocol byte. Next, let's go through normal stimulus and response for the TTL field and IPv4 packets. Now, in this case, we have system A, and it's sending a packet out to something out on the internet. We don't have that destination shown here. We're really only showing the first few hops, the first few routers that packet might go through. Now, for the most part, systems are going to be configured with a default time to live value. That's going to be different. Windows systems typically have one value, and Unix systems typically have another, and it doesn't really matter what it is, although you can use that to profile the source of a packet by looking at the TTL value relative to a number of preset values. But all that said, for our example here, we'll say that system A has set a starting TTL value of 128 and sent that to its destination. Now, router A is going to receive that packet, and it's going to do some of the rewriting we talked about earlier, where it's rewriting the source address so that the other routers know how to send data back to it. It's also recalculating checksums. Part of that checksum recalculation is also because the TTL value has been changed. And in this case, we're going through one router. It's going to be decrementing that TTL value by 1 to 127. So then when the router A sends its packet on further on along the line to its destination towards router B, the TTL value will now be 127. That will be one lower as it's gone through one hop. The same thing will happen with router B. In this case, router B will decrement 127 to 126, and the packet will then continue going on. And this will continue through each hop or each routing device that the packet goes through. Ideally, it reaches its destination as quickly as possible. If for some reason it doesn't, then the TTL is decremented to 0. Then we have a situation that's not ideal, and we have a different set of circumstances. So let's talk about that set of circumstances. In this case, we still have system A, router A, and router B. But let's say that system A were to send a packet with a TTL of 2. That's not a very common thing, but we have it here. TTL of 1 is a common thing, or lower TTL values using the traceroute tool, which we'll talk about when we talk about ICMP a little bit later in this section. But TTL of 2, so we see that packet would get to router A, and router A would decrement it to 1, and then it would send the packet to router B. Now, router B is going to get that, and it's going to decrement the TTL to 0. So what happens when the TTL gets to 0? Well, that's an interesting thing. One, as we mentioned, the data gets dropped. The packet gets dropped completely. It's not going any further. This is the end of the line for it. However, router B is obligated at that point to send an ICMP message back to the original source indicating that this has happened. That way the source knows it needs to retransmit data or have some type of application layer protocol handle this exception in some way. And it's going to do that by using ICMP. And again, we've not talked about ICMP. We'll talk about that a little bit more in depth later, but it's a utility protocol, and it's going to send a type 11 code 0 message, which means time exceeded, and TTL exceeded, essentially saying that the packet never reached its destination and was halted somewhere in transit. So that ICMP message will be sent back. It may not always be received by System A. Some intermediary devices will not forward these ICMP requests along. Some will not generate them at all. There's a little bit of practice versus theory that comes into play there. But for the most part, this is the normal stimulus and response, is that the terminal router of the connection will send an ICMP type 11 code 0 message back to the source system. This is actually a functionality that we'll use purposefully when we talk about ICMP traceroute in that section later on. But for now, know that this is what happens when a TTL does reach 0 and the packet can no longer move forward. I've switched over to a Wireshark window here because I want to show you an example of the TTL being decremented. I've actually, in this case, crafted an ICMP packet and sent it from one host to another. And I've captured both on the source and on the destination. And I want to compare those two TTLs. In this case, we have packet 1 here, which is going from 10.10.0.3 to 192.168.0.128. Now, if I expand the IP header here, we see we have a TTL value of 128. So that's the initial TTL that was specified by the transmitting host. Now, we have a reply to this, but we're not concerned about the reply. We actually want to see this same packet, but we want to see it as received by this 192 device. And from that, we should be able to tell actually how many hops it went through. So I'll switch over here from ipttl source.pcap to ipttl dest.pcap. Again, the exact same packets, but captured at 2 different locations. So here, I'll expand the IPv4 header, and we'll look at the TTL value, and we'll see here it is actually 127 now. It's been decremented by 1. So same packet, but we have a TTL that is 1 lower when it reaches its destination. So from that, I would ask the question, how many hops or how many routers were between these 2 hosts? Well, you guessed it, it's 1. The TTL decremented by 1, it went from 128 to 127, so there's only 1 hop between 10.10.0.3 and 192.168.0.128. If there had been 2 routers, we would have seen 128 decrement to 126 and so on. But in this case, there's only 1 router between them separating these 2 devices, and that 1 hop is reflected by a single decremented value from the TTL. The very last field we're going to talk about in the IPv4 header is the protocol field, and it's one we've actually already discussed a little bit if you followed along in our earlier examples near the beginning of the course when we talked about dissecting protocols and the encapsulation thereof. And the protocol field is important because it tells the system that is reading the packet what protocol to expect next, what the encapsulated or embedded protocol is. In this case, it's typically going to be a transport layer protocol, although it might also be ICMP as well, but it's really just what the next protocol header is. It's telling the system what to expect, how to parse the very next thing, and that's located at IP9, or the 9th byte offset from 0. You see that in the third row there, between the time to live value and the header checksum. So this is a pretty simple field. It's a 1 byte field, and it has a predefined set of values for a few common things. There are a lot of these values out there. Some of the more common ones you'll see are ICMP, which is 1, TCP, which is 6, and UDP, which is 11. Of course, these are maintained, as many of the things we've discussed are, by the Internet Assigned Numbers Authority, IANA, and there's a link here on the screen where you can go and actually view some of these. So you'll see a few different ones beyond these. Obviously, just different tunneling protocols, security protocols, things of that nature. There are a whole lot of them, but knowing how to interpret this field, knowing where to go to reference these numbers to look them up, is really going to be your best bet. I don't expect you're going to memorize a lot of them beyond the 3 that are on the screen here. You probably should commit those to memory, but for the most part, anytime you encounter one you don't know, you're probably going to end up Googling it and saying, what is the IP protocol field 47? What does that mean? Or just having this bookmark handy and going to it through there. Before we depart the IPv4 header, I want to show you just a couple of examples of the protocol field in action in these headers. Here we're looking at a file we just looked at when we talked about the TTL field. We see in the protocol field here, we see it says ICMP, so that's the highest level protocol header that exists here, and we see that on the bottom in the packet details view, so that's consistent. I'm going to go ahead and expand the IPv4 header, and if I do so, you'll see that the protocol field here is set to ICMP or 1. That particular byte is highlighted down here, which is just hex 01. So that's telling us we have ICMP as the next protocol that the receiving system would have to dissect. With that said, I'm going to switch over here to another packet capture I have open. This one's called DNS Query Response, and you guessed it, it's a DNS packet. We've not talked about DNS, but DNS relies upon the UDP transport layer protocol. We see that listed in here. UDP is embedded within IP, which has DNS data within that. Now, if I expand the IPv4 header here, we look at the protocol field, we see that UDP is listed, and that is the decimal value 17, the hex value 11 here. So some people prefer to refer to those in decimal. I refer to them in hex because most of the time I actually have to get that far into it. I'm probably looking at them in hex. But in this case, it's hex 11 or decimal 17, and that tells us we have UDP traffic that's embedded and is the next protocol here. So that's really the protocol field. Pretty straightforward, one of the more simple fields, but one of the more important ones when it comes to dissecting packets. Most of your tools like Wireshark and such are going to do that work for you, but if you are encountering an unknown protocol, you might have to look that number up yourself and do a little manual dissection that we've already talked about. But that's really the IPv4 header. Again, the workhorse of the internet, of network communications. Not overly complex, but there is a little bit to it. Most of the fields here, I think as you interact with them more, you'll begin to commit to memory. And again, we tried to focus specifically on the practical ones that I think are going to matter the most to you. If you're interested in learning more about some of the fields we didn't talk about, make sure to check out the RFC that was mentioned at the beginning of the IPv4 section.